There's a number hidden in every atom, quiet as a watermark, that decides how tightly electrons cling, how brightly stars shine, and how chemistry composes life. Physicists call it the fine structure constant, alpha, written A. It isn't measured in meters or volts. It has no units at all, a pure ratio, roughly 137.035999. Change it a little and the universe plays a different score. Alpha bundles together fundamental quantities into a single dial, the electron's charge, e.g. Planck's constant, the speed of light, and a geometric factor of, with nu in SI units, with in the combination RLE2 4p easier HC sets the strength of electromagnetism. The force that binds electrons to nuclei makes atoms radiate and drives nearly every technology built on electricity and light. Because R is dimensionless, it carries a special weight. Rulers and clocks can be redefined. Pure numbers cannot. If a civilization in some distant cosmos also has light, charge, and quantum mechanics, they could compare their R to ours. The name fine structure points to its first starring role. Early spectroscopists split starlight and lampglow into sharp lines, atomic fingerprints. Look close, and each line isn't single. It's finely split into a tight double, triple, or quadruple. In the 1910s, Arnold Sommerfeld extended Bohr's atom with relativity and found that the size of these splitting scales like A2. In modern quantum mechanics, R slips into the Hamiltonian and slightly shifts electron energies. That slightness sets everything. The Bohr radius, the natural size of hydrogen, scales like 1O. Binding energies scale like R2. Radiative rates scale like higher powers of A. The shape of the periodic table and the resilience of chemical bonds are not accidents. They're tuned by this one number. Twist the dial and the world tilts. Make a larger, say closer to 100, and electrons feel a stronger pull. In heavy atoms, inner electrons already whip around with relativistic speeds. Increase A and relativistic effects explode, rearranging the order of orbitals and destabilizing parts of the table we take for granted. Shrink R toward 200 and atoms loosen, molecules turn fragile, fusion thresholds in stars shift. Long-lived carbon chemistry becomes harder to sustain. A few percent either way, and a star's chemistry and perhaps life take unfamiliar forms. That's why A-Ant has been called the most dangerous number. It sits where the universe works. The mystery isn't that it matters, it's that we don't derive it. We can measure it to absurd precision. We can calculate its consequences with stunning success. But why this value? Wolfgang Pauli kept the number 137 close to his mind like a riddle and, legend says, died in hospital room 137. Richard Feynman called A magic number and joked that every theorist should scribble it on the wall and worry about it. Arthur Eddington once argued that R1 should be exactly 137, anchored by deep mathematical reasoning. He was wrong. Experiments pin it a little higher with crucial decimals. Nature doesn't bend to elegant numerology. It demands mechanism. Mechanism arrived as quantum electrodynamics, QED, the quantum field theory of light and charged matter. In QED, R is the coupling constant. the probability amplitude that an electron emits or absorbs a photon. Write down the Feynman diagrams. Each vertex that joins an electron line to a photon carries a factor of A. The entire calculation becomes a power series in R. This picture brings a second, deeper twist. R isn't perfectly constant. As you probe shorter distances or higher energies, the quantum vacuum seethes with virtual particle-antiparticle pairs. These blips polarize the vacuum, screening electric charge. The result, measured in colliders and precision experiments, is that R runs with energy, at atomic scales, R1 on 137, near the mass of the Z boson in particle physics, R1 128. Push to fantastically high energies, and the math hints at a Landau pole, a sign that bare QED must be embedded in a larger framework before that scale, another clue that A story is part of a wider tapestry. How do we measure a number this slippery with so many decimals? Several routes converge. One of the cleanest comes from the electron's anomalous magnetic moment, written Ag 2 QED predicts a series for G from 2 with coefficients that depend on A. Measure AG2 exquisitely well, compute the series to eye-watering order, invert the relation, and you extract A. Another road uses atom interferometry. Cold atoms recoil when they absorb and emit photons. Interferometers measure that recoil frequency with mind-bending precision, linking it to Ham and to R through other constants. There's also the quantum Hall effect, where conductance plateaus appear at values involving A2, He, combine with other constants, and you triangulate R again. The fact that multiple independent methods agree across continents, laboratories, and techniques is one of the quiet triumphs of modern physics. A different question lurks at cosmic scale. Has it always been the same? Because R is dimensionless, it's fair game for comparisons across space and time. Two natural experiments do the asking. The first, the Oklo natural nuclear reactor in Gabon, where uranium deposits went critical 2 billion years ago. The isotopic leftovers act like a fossil spectrometer. Their action rates, they imply, would have shifted if A were different. Analyzers find no evidence for change beyond tiny bounds. The second, quasar absorption lines, fingerprints of intervening gas in the light from galaxies billions of light-years away. Some studies once hinted at spatial gradients in A at the level of a few parts per million. Others found no such effect. Today's best constraints suggest any variation is smaller than a few parts per million over most of cosmic history. If it drifts at all, it drifts very, very slowly. Pull the camera back further and it becomes a character in the unification story. At ever higher energies, the 3-gauge couplings of the standard model, strong, weak, electromagnetic, run toward each other. In some extensions of the theory, like supersymmetry, they nearly meet. At a grand unification scale, a hint, not a proof, that all forces may be faces of a single interaction at energies far beyond any machine on Earth. In that view, R at low energies isn't fundamental by itself. It's a low-energy echo of deeper symmetries broken as the universe cooled. The decimals we measure could be boundary conditions set in the first instance after the Big Bang. For all the poetry, R is also just workhorse physics. It sets the Mark-Thompson cross-section that tells photons how to scatter off electrons. It enters the von-Rydberg constant that pegs spectral lines. It appears in formulas for Compton scattering, Bright-Wigner widths, vacuum polarization, and in radiative corrections in nuclear and particle processes. When astronomers extract elemental abundances from starlight. When chemists compute bond energies with quantum chemistry, when engineers design lasers and detectors, they are in practice using Eki whether they write it down or not. Perhaps the strangest allure of 137 is cultural. Painters have smuggled it into canvases, novelists use it as a cipher, internet forums spin it into prophecy. Physicists don't begrudge the mystique, but the discipline of physics is to turn mystique into math. The number on the wall becomes lines in a Lagrangian, loops in a diagram, digits in a measurement banded with uncertainties. The fascination endures not because R is magical, but because it's both. Simple enough to write on a napkin and deep enough to connect laboratory precision to cosmic history. Here's the thread to hold for the rest of this episode. Alpha is a coupling, a measure of how strongly light and charge talk. It is dimensionless, making it the kind of number that might carry meaning across universes. It runs with energy because the vacuum is active, not inert. It is measured by multiple independent clocks that agree, and its value sits in the narrow corridor where chemistry thrives. That corridor might be an accident, a selection effect in a huge multiverse, or a clue to principles we haven't uncovered yet. In the next chapter, we'll open 3 doors at once, how A threads through spectacular precision tests like the electrons G2, how grand unification dreams try to explain why. It takes the value we see and how close we've come, if at all, to signs that R may shift in extreme environments where space-time itself is stretched. Keep the number in your head, 137. Not as a talisman, but as the voice of electromagnetism speaking in pure ratio. At laboratory scales, alpha reveals itself through one of the most precise confrontations between theory and experiment ever staged, the electron's magnetic moment. A classical spinning charge has a magnetic factor, G=2. Quantum electrodynamics corrects that value by an amount called the anomaly, AE=G22. Draw the Feynman diagrams, 1 loop, 2 loops, up to 5 loops and beyond, and you get a power series with coefficients that have been computed by armies of theorists over decades. Trap a single electron in a Penning trap, coax it to flip its spin and cyclotron states, and infer G to parts per trillion. Invert the theoretical series with that measurement, and A falls out with astonishing precision. It's not a single experiment that wins the day, it's a cross-check tapestry. Atom interferometry reaches R by measuring how a cold atom recoils when it absorbs and emits photons, linking recoil frequency to H-rem and then to A through other constants. Quantum Hall and Josephson effects tie conductance and voltage standards to E and H different roots, different systematics, same number within error bars. That agreement is physics at its most convincing, independent clocks ticking the same seconds. Precision, however, doesn't mean immutability. In quantum field theory, couplings are scale-dependent. The vacuum is not empty, but a polarizable medium. Virtual electron-positron pairs screen electric charge, so the effective strength of electromagnetism depends on the momentum scale μ at which you probe it. Renormalization group equations capture this evolution. To first approximation, one writes M1 with B a constant fixed by the field content. For QED, this implies AE grows slowly with energy. At atomic energies, A1 137.03599. By the Z boson mass scale, A1 is closer to ER's 128.129. Keep cruising to absurd energies, and the running suggests a Landau pole, an unphysical divergence, signaling that QED alone cannot be the whole story to infinite scales. In practice, the standard model's full set of fields takes over. At yet higher energies, new physics must enter, or the theory is ultraviolet incomplete. Either way, the moral is the same. R is a low-energy face of a deeper structure. The running of couplings becomes a map toward unification. Plot the inverse couplings of the strong, weak, and electromagnetic forces against ln m. The lines tilt because each coupling runs with its own slope. B. In the minimal standard model, the three lines almost, but not quite, meet. In supersymmetric extensions, adding partner fields changes the slopes so that the lines nearly intersect at a grand unification scale around 1016 GeV. That hint isn't proof, it is a suggestive alignment that says the low energy values are boundary conditions set by high energy symmetry breaking. In that story, R is not arbitrary. It's the cooled remnant of a single unified coupling filtered through cosmic history. The number 137 surfaces again in a very different corner. The Dirac equation for an electron in the Coulomb field of a heavy nucleus. For a point-like nucleus of charge, Z, the ground state solution behaves oddly as ZAR approaches 1. When ZAR and GT1, the 1's level dives into the negative energy C of the Dirac spectrum. You enter the regime of supercritical fields. Real nuclei have finite size, so the threshold is higher, around Z-SAUT 170 in detailed models. But the moral remains striking. The product ZAR is the control parameter. This mathematical cliff has physical consequences. When two very heavy nuclei graze each other at low relative speed, they can form a transient quasi-molecule whose combined Z is supercritical. Theory predicts the vacuum becomes unstable and emits positrons as bound electron states spill into the continuum. Experiments have chased signatures of that effect in uranium-on-uranium collisions and related systems. Whether or not the cleanest smoking gun has been seen, the logic is crystalline. 137 marks a frontier in relativistic atomic structure, where the strength of electromagnetism measured by A collides with the speed limit C baked into the Dirac equation. If A is scale-dependent in theory space, a natural suspicion arises. Could it drift in real space or time? Dimensionless constants are the only sensible targets for that question, and R is Exhibit A. Two natural laboratories anchor the limits. First, the Oklo natural fission reactor in Gabon, where groundwater moderated uranium ore 2 billion years ago. The neutron capture resonance of samarium-149 is exquisitely sensitive to A. The isotopic leftovers in Oklo's rocks imply that if A has changed, the shift is smaller than parts per 10708 over that span. Second, the cosmos itself, spectral lines from gas clouds backlighting distant quasars. The many-multiplet method compares transitions with different eye sensitivities to hunt for ppm-level drifts. Some early analyses reported tantalizing hints of spatial gradients. Later reanalyses with improved systematics found null results. Today's consensus: any variation is tiny if it exists at all. Closer to home, state-of-the-art optical clocks, ytterbium versus strontium, aluminum versus mercury ions, compare transition frequencies with sensitivity to A at parts in 1018 per year. The current limits say A's time derivative is consistent with 0 on human timescales. Extreme environments test QED in other ways. Around magnetars, magnetic fields approach or exceed the so-called critical field, BC. 4.4 109T, at which QED predicts vacuum. Birefringence, light polarized along different directions, propagates at slightly different speeds through the magnetized vacuum because of virtual loop effects. X-ray polarimetry and optical observations of neutron stars probe that subtle splitting. Heavy ion collisions at accelerators briefly generate electromagnetic fields strong enough to nudge similar nonlinear QED phenomena. These effects are not a change in A per se. They are A-powered loop corrections becoming visible when fields approach the natural scales set by μ, c, and h. The constant stays the same. The vacuum's response shows new facets. If measurement and running tell us how A behaves, the deeper itch remains. Why? That value. Several broad strategies compete. One is dynamical. Derive A from a high-energy theory where the unified coupling and symmetry breaking pattern fix today's low-energy constants. Grand unified theories, string compactifications, and related frameworks try to compute that map. Another is environmental. If a larger landscape of vacua exists, each with different constant values, then observers will arise only in pockets where chemistry and stellar physics behave, an anthropic selection. In that view, A's value is less a theorem than a filter. A third strategy is to treat A as the vacuum expectation value of a field, sometimes called a dilaton, that could, in principle, vary slowly in space or time. Tight limits from clocks and astrophysics then trap such models in narrow corners of parameter space. None of these answers has locked in a consensus. That is both frustrating and liberating. The door is still open. Back on the ground, A quietly rules everyday technology. The stability of lasers depends on transition line widths that scale with A. Detectors calibrate using photoelectric effects and Compton scattering where R sets cross-sections. Quantum chemistry codes approximate electron correlation atop a Hamiltonian whose coefficients whisper R. Astronomers infer stellar temperatures and compositions from spectra whose absolute positions depend on a Viether-Rydberg constant and fine structure corrections. Metrology itself, the science of measurement, leans on universals that triangulate A. Since 2019, the SI has defined E, H, and C as exact. That choice turns A into a bridge between electrical standards, Josephson and quantum Hall effects, and mechanical optical ones, Kibble balances, optical clocks. The web of constants is tighter than ever. R is the knot that ties light to charge. History adds human texture to this sterile precision. Sommerfeld's early insight that fine structure would scale with A2, Dirac's merging of quantum mechanics with relativity that put Tsar at center stage, Schwinger's first-order correction AE equals A to P that launched the modern triumph of QED, Feynman's path integrals giving a new language to the same facts. Dyson's warning that the perturbation series in powers of A is likely asymptotic rather than convergent, perfect to a point and then divergent if you push orders too far. Even the SI redefinition story loops back. By fixing E and H, we elevate certain constants to axioms and ask others, like R, to become measurements that audit the whole edifice. A constant can be dangerous in two senses. Dangerous because a tiny change would have burned the periodic table to ash. Dangerous because it tempts beautiful but wrong theories. Eddington's integer, Pauli's superstition, decades of numerological attempts to conjure 137 from pure math, each is a cautionary tale. The way out is always the same: measure, predict, compare, repeat. Alpha has rewarded that discipline with jaw-dropping agreement between theory and experiment, and with just enough mystery left over to keep theorists honest. Before moving on, hold 3 images. First, the penning trap, where a lone electron's dance writes digits of A on a screen. Second, the renormalization group flow, 3 slanted lines almost converging in the ultraviolet, whispering about unity behind diversity. Third, a heavy nucleus, its Coulomb field so intense that Tsar brushes 1, the number 137 surfacing not as mysticism, but as a physical threshold in relativistic quantum mechanics. In the next part, we'll connect these images to the broader question of naturalness, why some constants look finely adjusted, how A intertwines with others, like the electron-to-proton mass ratio and the weak scale, and whether dangerous numbers point to deep principles or to selection effects in a multiverse. We'll also explore a counterintuitive point. The most universal constants might be the ones you never think about, until a precision experiment nudges their last digit and the entire theoretical house shifts by a millimeter.